So this is physics. We are nearing the end of Unit 3, and now we are going to be talking about forces on an incline, or ramp problems. Ramp problems are another topic that probably could be its own unit, but it falls well into Unit 3. So we've considered several examples of forces being applied to objects. So horizontal surface, here's an object without friction. So there's a force exerted on it, and there is nothing opposing it, nothing in the opposite direction. In this one, we have a horizontal surface, and we have friction. So here's the force pushing, and the friction is acting in the opposite direction. In this one, we have a horizontal surface, but the force is being exerted at an angle. And remember, we did these with the little red wagons earlier. Only the force in the direction of motion, only the force in the direction of motion acts on the object. The horizontal component is producing the acceleration. The upward force is really just kind of wasted in that situation. And then we have forces that are applied vertically. So in our rocket problem, we have the thrust, which is pushing backwards, and the ground is pushing back on the rocket, and we may have some acceleration. So now we're going to look at forces being applied to objects that are sitting on an inclined plane, or a ramp. So when a box is positioned on a ramp, there are three forces that we have to consider. So the three forces are, number one, the force of gravity, which is the weight, pulling down towards the center of the earth. This is the weight. So if you look at these diagrams, the weight is pulling down towards the center of the earth. That would be this one right here in the first ramp. It would be this one in the second ramp, and this one in the third. All of these are pointing directly down towards the center of the earth because weight is directed straight down. The second thing is the component of the weight which is directed parallel to the plane. And this one is called the force parallel. So this is the gravity pulling the box down the ramp. So in our pictures up here, in our first ramp, the force parallel is parallel to the surface of the ramp. So here's force parallel. In the second one, the force pulling it down the ramp, which is parallel to the ramp, is force parallel. And in this one, we have a much greater force parallel pulling it down the ramp. Remember, the length of the vector indicates magnitude. We'll even write that down. The length of a vector represents magnitude. So we have three ramps here. In the first ramp, which is not very steep, the force parallel is pulling it down the ramp to a small degree. On the next ramp, it is steeper. The force parallel is greater than in the first situation. So there is more of a force trying to pull it down the ramp. In the third one, we have a very steep ramp, and the force parallel is very great. The force trying to pull it down the ramp is the greatest in this one than either of the other situations. The third one is the component of the weight which is directed normal, which means perpendicular, to the plane. Normal is a term that means perpendicular or 90 degrees. So the component of the weight which is directed perpendicular to the plane is written like this. This is the force perpendicular, or the perpendicular force. This is the part of gravity pulling the box against the surface. So we have the weight. Part of the weight is pulling it down the ramp, and part of the weight is the force perpendicular, which is pulling the box against the ramp. The second one, here is the weight. Here is the force of the weight trying to pull it down. Force perpendicular is the component of the weight holding it against the surface. And the third one, very steep ramp. The perpendicular force is very small compared to the other two. The force pulling it down the ramp is greater than the force holding it against the ramp. So when an object sits on an inclined surface, gravity pulls on the object down the incline and against the incline. So these pictures show why a ball rolls down a hill, why it's hard to push a wheelbarrow up a hill, and why you could put your car in neutral and coast down a hill, which is not recommended. In some places it could be illegal. It's because of the component of the object's weight, which is parallel to the ground. In the above diagrams, notice that as the ramp gets steeper, the component parallel to the plane, which is the force parallel, becomes larger. As we get steeper, the force parallel becomes larger. And the component normal to the plane, or the force perpendicular, becomes smaller. When we consider pulling the wagon handle at an angle, we will separate the force, or the pull, into the horizontal, or the force in the X, and the vertical, the force Y components. In ramp problems, we will separate the weight vector into its two components. We need to find the parallel force and the perpendicular force. Example 1, a 200 kilogram box rests on an incline of 20 degrees. Find the perpendicular force and the parallel force. So the first thing that you'll want to do is draw a picture. So if this is the horizontal surface, and here is the incline is 20 degrees. And let's go ahead and make this a right triangle. So we've got a vertical and horizontal. And we'll put our object on here. So here is the object. It is a 200 kilogram box. And the first thing we'll do is find the weight. So this is the weight So that's Fg, the symbol for weight. And it is 200 kilograms in mass times 10 for gravity. The weight here is 2,000 newtons. We can split this into its component vectors. So if we, let's see here, we'll make the force parallel, and it goes parallel to the surface. And we want to make sure the magnitudes are about in the right spot. Here's this. So this is our parallelogram. It's basically working backwards from when we found the sum vector. So the weight is the sum vector here. And so this one will be the force that is perpendicular, the force that is holding it against the ramp. This one is the force parallel, which is the force that is trying to pull it down the ramp. Okay, so what we have here, let me change color so we can see a little better. This is a right triangle. And we know the hypotenuse of this right triangle, which is 2,000 newtons. Find the force perpendicular and find the force parallel. So we are looking for two sides of a triangle, and this angle right here, if you look at this carefully, these are similar triangles, and so the angle here is 20 degrees, just like the angle over here is 20 degrees. And so we have a 90-degree triangle with a 20-degree angle on the other end. And so let's look for the perpendicular force first. Here's the perpendicular force. Here's the angle we know. This is the adjacent side, and we know the hypotenuse. So if we use cosine, it relates the adjacent and the hypotenuse. The cosine of 20 degrees equals the force perpendicular, that's this one, the adjacent side, over the hypotenuse, which is 2,000 newtons. So rearranging this, we have force perpendicular equals 2,000 times the cosine of 20 degrees, which tells us the perpendicular force is 1,879 newtons. For the force parallel, we are looking for this component, and this is a parallelogram, which means that the force parallel here is equal to this side of the triangle at the bottom. So here's our angle, is 20 degrees. We're looking for the opposite side, and we have the hypotenuse, so we use sine. The sine of 20 degrees equals the opposite side over the hypotenuse, which is 2,000. Force parallel is 2,000 times the sine of 20 degrees. And so this force is 684 newtons.